Okay, so we're going to find eigenvalues and associated eigenvectors for this 3 by 3 matrix. So all the examples we've looked at so far are only 2 by 2 matrices. So we're going to start the same way. We start with all of the problems. So this is our matrix A, so we want to write down A minus lambda I. So we're going to be multiplying the appropriate size identity matrix, 3 by 3 identity matrix, by lambda, and then subtracting that from our matrix A. So the effect will be that I just end up subtracting lambda on the main diagonal. So at this point, you should not need to write out a couple steps for that. You should understand that this is going to have the effect of subtracting lambda on the main diagonal. And just be able to write this down in one step like I did. When we first did these, we wrote out a couple steps for that so that we were clear about what was happening. All right, and then we want to take the determinant of this matrix and set that determinant equal to 0 to find the eigenvalues. So when you find the determinant, you're going to have to do this determinant by hand because it's not all just constants in here. So when you find this determinant, you want to be strategic about that. You want to notice that you've got a row that's got a lot of zeros in it and also a column that's got a lot of zeros in it. So I'm going to expand along this bottom row here. So when I think about doing that, so the determinant of A minus lambda I. So when I think about doing that, remember you need those alternating signs, the part that comes from the -1 to a power in that summation form that we looked at for the determinants. So if you think about those, we also talked about kind of using that checkerboard pattern and thinking about that as a way to figure out what the signs are, the plus, minus, plus, depending on where you're at. So in thinking about that, since I'm going to expand on the bottom row here, I'm going to think about just starting in the upper left corner. So just thinking about signs here, that would be plus, and then it's just a checkerboard pattern. So plus, minus, plus, minus, plus is what I am going to need here. All right, so this part for my determinant will end up being 0. So I'll have plus 0 times the determinant of what's left when I eliminate that row and column. That's all just going to be 0. Minus 0 times the determinant of what's left when I eliminate that row and column. So that's because I'm going to multiply by 0, that's still going to be 0. So I don't really need to write that. And then 13 minus lambda times the determinant of what's left when I eliminate that row and column. So I am going to have to do a little algebra here. So I'll have 25 minus lambda times -5 minus lambda minus -12 times 18. Okay, so I want to set that determinant equal to 0 and solve for lambda. So you want to be smart about that. When you have an equation equal to 0, you would like it to be factored. And I already have this partly factored, so don't unfactor the part that's already partly factored. I have this factor of 13 minus lambda here. Remember these terms. 0 out. So I have this factor of 13 minus lambda there. And then for this part, you'll probably need to go ahead and multiply that out and then refactor that. So I'm just going to write a little scratch work here to save some space. So when you FOIL all this part out, multiply this, and combine like terms, I will just write above here what you get when you do that. You will get lambda squared minus 20 lambda and plus 91. Probably use a calculator to do a little bit of that arithmetic. All right, so that's what I'm going to get when I multiply this all out and combine like terms. And then I want to factor that. So 91 is 13 times 7. So this factors into lambda minus 13 times lambda minus 7 from all this part. Okay, so I have 3 eigenvalues here. 3 by 3 matrix will have 3 eigenvalues, but one of them is repeated. It has multiplicity 2. So I have lambda equals 13 of multiplicity 2, and lambda equals 7. All right, so those are my eigenvalues. Write that over here. And what we want is eigenvectors associated with those eigenvalues. And ultimately, we're going to be using this to solve some differential equations. So there's a lot of things you might ask and questions that you might answer about those eigenvectors. We're going to defer those until we're ready to solve some differential equations using those eigenvectors. All right, so I really have two different ones to think about here. The fact that this one has some multiplicity might mean that it might behave a little bit differently than the other one. And if you were in a linear algebra class, it might mean that you have a little bit more to think about with this one. But for our purposes here, we really just have kind of now two different sub-problems to do. So I'm going to do those in a different colors here so we can focus on each one of those separately. All right, so for lambda equals 13, I'll start with that one first. All right, so to find the eigenvectors that go with lambda equals 13, the first thing that I want to do is put in 13 to my a minus lambda I. So I'm putting in 13 for lambda here. So 12, 12, 0, negative 18, negative 18, 0. And then the bottom row will all be zeros. All right, and what I want to do is find a basis for the null space of this matrix. So we've worked with null spaces, we've worked with systems of equations. So what I'm looking for is a basis for the null space of this matrix. So when I think about the null space of that matrix, I would be looking for a vector, a 3x1 vector, that when I multiply it by this matrix, I would get the 0 vector. So you don't always have to write this step out, but because we've really just kind of started with eigenvalues and eigenvectors, I'm going to go ahead and write that out for this one. So what I'm looking for is a 3x1 vector. So I just put 3 unknowns in there, x, y, z, so that when I multiply this matrix by that vector, I get the 0 vector. That's what it means to be in the null space. You get the 0 vector when you multiply by that. So essentially what I'm doing is solving a system of equations. If you do this matrix multiplication here, you get 12x plus 12y plus 0z, negative 18x minus 18y plus 0z, and then 0x plus 0y plus 0z, and then all equal to 0. End up with this homogeneous system of equations. So you can think about some things that you already know about solving systems of equations and leverage that to solve this system. You can put this matrix in and do a reduced row echelon form if you would like to do it that way. This is a simple enough one you might be able to just think about it and think about what those solutions are going to be like. So when you solve this system, you're going to have 12x plus 12y equals 0. And negative 18x minus 18y equals 0. Those are redundant. Those are really the same equation. If you divide through by 12, divide through by negative 18, you get the same equation. So you essentially end up with the equation x plus y equals 0. There's no equation that involves z, but z is an important variable here. And then the other two equations will zero out. So you're going to have both y and z being free variables. Okay, so I'm going to let each of those be a parameter. Y equals, say, t. And z is a free variable, so z equals u. And then I'm going to write my x in terms of that. So my solution for this system here, I'm going to get x equals negative t, y equals t, and z equals u. If I want to write that in terms of a vector, so that I'm thinking about a basis for the null space, then I can write this as a linear combination of two vectors, so that I have t times the vector that would be the coefficients of the t's, negative 1, 1, 0, plus u, and then the vector that's the coefficient from the u's, 0, 0, 1. Okay, so I have this two-dimensional null space, and these two vectors are a basis for that null space. So I'm going to write that as like we've written some bases, b equals for a basis. In your homework, they will probably just ask you to write down these two vectors, not as a set containing two vectors here. These are not the only two vectors. Remember that any vector space has really infinitely many different bases for that vector space. So this is just a basis for that null space, but this is a complete set of eigenvectors for this eigenvalue. All right, I still have one more to do, so I'm not going to write out as much work for that second one. I'm just going to write down our vector and kind of what we get from the system. But the basic idea is still the same for the second one. These are the eigenvectors associated with lambda equals 13. And then I also have some eigenvectors that I need to think about that are going to be associated with lambda equals 7. All right, so I'm going to be putting 7 into my matrix over here. All right, and again, what I'm going to be looking for here is a basis for the null space of this matrix. So the same way I did up here, I'm going to take this matrix times some arbitrary vector of unknowns, x, y, z, or a, b, c, or whatever letters you want to put there, times that matrix equals the 0 vector. And what I get is a system of equations. And so you can kind of think about maybe what that system of equations is going to be like. I'm just going to go ahead and write down what you would get from that resulting system of equations. You can also use a reduced row echelon form of this matrix here. So if you do a reduced row echelon form, you will get x plus 2/3 y equals 0. You'll get another equation that is z equals 0. And then the third equation will drop out. So the last row of the matrix will be just be 0, all zeros. All right, so here you really just have one free variable. Z is fixed to be 0. Y is a free variable. So you can let y be t, right? X in terms of t. And then what you're looking for is your solution written as a linear combination of those two vectors. So for this one, the vector that you're going to get, so I would have x equals negative 2/3 t. So t times negative 2/3. Y is t, and z is 0. So this is a basis for this eigenspace. All right, and on the online homework, it should recognize that as a perfectly fine answer. If you look at the solutions, though, and you ask it to show you the answer or show you the examples, textbooks often like to make eigenvectors so that the first entry is positive and not a fraction. So you can take scalar multiples of this one and or this one and rewrite it so that you end up with an equivalent basis. It's a different basis, but it generates the same space, but that has a little bit nicer coefficients. For our purposes, it's not necessary that you really do that, but I just want to point out that when you look at those solutions, you might see that they have a scalar multiple of whatever you have written down, and that's perfectly fine. It's just a choice that you make at that step in the problem. All right, one other thing I want to say about this is that any little mistake at any point in the problem can totally send this off in the wrong direction. So if you write down the original problem wrong, if you make a sign error when you write down this, if you make an algebra error here, it can make everything completely off base. So don't get too frustrated about that. Just try to check back through your work. Remember that if the algebra is coming out super, super crazy, maybe it's not in the right direction in real life. You might have matrices with eigenvectors and eigenvalues that are super crazy, but in our homework, for the most part, they try to make the numbers nice, whole numbers, positive or negative whole numbers. Maybe you end up with some fractions in your matrices here, but they're not terrible fractions. So if things are getting too crazy, take a step back, double check that you didn't just make a mistake writing the problem down correctly. I know it can be frustrating, but send me a picture if you need help, and I can probably find your mistake pretty quickly. All right, try some homework.